Thank you very much. So, as the extended title says, the talk is based on a joint work with progress with Maxim, which has a kind of a bigger title, holomorphic Fuller quantization, and just one section of it, but hopefully it will be clear why the bigger title is called holomorphic Fuller quantization. So I start with the history and the motivation for what's going on, but before I should say that there was kind of a long-standing question about the relation, the similarity between deformation, quantization, and Fukaya categories, and it's kind of one piece in that picture. But let's first very briefly review the history of Riemann-Hilbert correspondence, sort of Wikipedia stuff. So classically, it relates algebraic vector bundles on a complex projective curve endowed with connections which have irregular singularities and finitely many points. We call it the RAM side of the Riemann-Hilbert, and the representations of the fundamental group of the corresponding punctured Riemann surface. We call it the Betis side. So in 70s, Deligne generalized this classical story to higher dimensional case and formulated it as an equivalence, the theorem about equivalence of the category of algebraic vector bundles in smooth algebraic variety with flat connections, blah, 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 and the category of local systems, locally constant sheaves. And in the 80s, Kashiwara provided much general statement about holonomic D-modules with regular singularities and constructible sheaves. So he constructed the Riemann-Hilbert functor. Everything starting with Kashiwara, everything was derived. So it's equivalence of derived categories of complexes of holonomic D-modules with cohomology, which are D-modules with regular singularities, and derived category of constructible sheaves. Also, it was observed in that time and proved by Kashiwara that the natural T structure, which consists of holonomic D-modules with regular singularities, under this equivalence, it goes to the category of perverse sheaves with the middle perversity. All right. So later, much later, a microlocal version of the result of Kashiwara was suggested by several people. Some of them are listed on the blackboard. And in that generalization, the modules, which objects which live on the manifold X, were upgraded to modules for the sheaf of microlocal operators, which live on the cotangent bundle. So it was known since Sato-Kawai and Kashiwara, since the 70s. But on the Betis side, the sheaf of microlocal perverse sheaves was introduced by Andronikov, Voshtis, McPherson, and Villanen, and actually just the same statement as was mentioned on the previous slide was upgraded to the statement of the cotangent bundle. Now, the notion of a microlocal sheaf, microlocal perverse sheaf, used the concept of a singular support of a constructible sheaf, introduced soon before that by Kashiwara and Shapira. It's a certain conic Lagrangian submanifold. And recently, actually, very recently, in the last 5 years. Saita and Sasha Davidson generalized, proposed generalization of this important geometric notion, which was pure algebraic, not transcendental like in Kashivara and Shidara. All right, so next step is a Riemann-Hilbert correspondence for irregular holonomic modules. So regular means that basically coefficients of differential equations have poles of order 1, and irregular means arbitrary poles with singularities. So this is more complicated because it involves certain Stokes data near singular points. In the case of, in one-dimensional case, complex curves and bundles with irregular connections, the equivalence of equivalence theorem was proved by William Lagrange in the 80s. On the Becky side, it involves not just local systems on the punctured curve, but also filtrations of these local systems assigned to which live on a small circle near singularities. So that's what I call Stokes data. A higher dimensional case, even more complicated, and it's really very recent. There is a list of people who contributed to different aspects of that, and a review, I think, can be found in the recent preprint and archived by Kashivara and Shapira, but I think actually it was proved by Aniola and Kashivara a few years ago. Anyway, all these statements, starting with the classical one and up to this irregular story, it's a certain equivalence of categories between holonomic D-modules and constructible sheaves. Now, aim of my talk is to relate that story to Fukaya categories. And from the point of view of the history of Riemann-Hilbert correspondence, the relation to Fukaya categories is not totally surprising. Indeed, by the work of, first of all, Kantsevich, and then Nadler, Zaslow, Abu Zaid, and others, some versions of the Fukaya category can be expressed in the language of constructible sheaves, which stays on the Becky side of Riemann-Hilbert correspondence. In particular, the definition of Fukaya category proposed by Nadler and Zaslow, I believe 7 years ago, in the case of the tangent bundle. Only describe the answer, actually provides an equivalence of the version of the Fukaya category with the category of constructible sheaves. Again, everything is derived. And there is a similar statement about wrapped Fukaya category of the cotangent bundle, which is due to Abu Zaid. In that case, the wrapped Fukaya category is expressed as a category of perfect modules for DJ algebra of negatively graded chains on the pointed loop space on the base. And for example, if the base X of the cotangent bundle is a KP1 space, so it's just it's the same in the derived sense as a fundamental group, and so we recover local systems again. All right, so then kind of a bottom line is that if we consider, for example, finite dimensional modules for the wrapped Fukaya category, then it should be a good candidate for the Becky side of the Riemann-Hilbert correspondence in general. Okay. A few more motivating remarks. So on the previous 3 slides, only constructible sheaves appeared, and you might get a feeling that constructible sheaves are more fundamental objects than the Fukaya categories, which is not the case. It's good for this conference. This is not as transparent if we work with the modules, but it will be clear. It is clear when we work with difference analogs, DQ modules, which mean that instead of differential equations which produce D modules, we work with difference operators which produce DQ modules. This theory is much more restrictive because we need an operator of shifts. Shift, it's not local. It exists basically on the tori, maybe at best in tori varieties. But anyway, the Riemann-Hilbert correspondence for DQ modules for difference equations on the Becky side, it does not have constructible shifts. It has, due to the work of Ramis, Saloy, and Jean, we see coherent shifts on the elliptic curve even in dimension 1, which means difference equations on C star. And the category which appears in the work of Ramis, Saloy, and Jean, it admits an interpretation in terms of an appropriate Fukaya category which is associated with the toric compactification of C star squared, so which plays a role of the cotangent bundle in the case of C star. All right, and one more optimistic remark for people who like Fukaya categories, like for example myself, that from the point of view of the equivalence functor in Riemann-Hilbert correspondence, remember there was this functor suggested by Kashiwara, this one, in one direction. In the case of, for example, irregular D modules, the functor in the other direction is more complicated, but from the point of view of Fukaya categories, the inverse functor can be put natural in the framework of family Floer homology. And roughly speaking, these D modules should correspond to constructible sheaves which arise as family of Floer homology of a certain Lagrangian submanifold with a variable fiber. People who know this Floer family Floer homology stuff recognize this Victoria. So, all right. Maybe one more thing which stays here. The D modules and the DQ modules which produce different type of answers, constructible sheaves and coherent sheaves, if you do not think in terms of Fukaya categories, they are both a deformation quantization of certain symplectic or Poisson manifolds. And therefore, one can hope that the Riemann-Hilbert correspondence should be put into the framework of deformation quantization, and this is indeed the case. So I start with a reminder or a collection of useful facts from the deformation quantization. Now, there are different versions of deformation quantization, so I should specify which one will be useful to me. So, in the case, so I will work with symplectic, complex symplectic manifold, which very soon will become algebraic symplectic manifold. An example is a cotangent bundle to an algebraic variety. So, conventional story of deformation quantization, in the case of the cotangent bundle, basically the answer is given by the sheaf of algebras of microdifferential operators. In the case of an arbitrary complex symplectic manifold, we have a sheaf of abelian categories over the ring of formal power series in the Planck constant. And this is a story which goes back to kind of the most the best approach is due to Kontsevich and then to Kashivara and Shapira. So in any case, since we work with sheaves of categories which are locally sheaves of modules which deform the sheaf of either analytic or regular functions in the underlying manifold, so then we can ask about the analog of the holonomic module. Because in Riemann-Hilbert we have all categories of holonomic modules, but it's clear how to define it, taking the reduction modulo the ideal generated by H. So then it can be defined classically. So then the holonomic module is the one which has modulo H support, which is a maybe singular complex Lagrangian variety. So all its smooth components are complex Lagrangian. So this is a nice notion, but this is not the one which I will be using today, because in the formal approach, the Planck constant is just a parameter. At best, we can, with some effort, we can speak about the argument of a Planck constant, but the absolute value is just a formal parameter. And I would like to have Planck constant to be a complex number. So for that, I will use another notion which was introduced by Maxime 17 years ago. It's a notion of semiformal quantization. In fact, for not necessarily symplectic or even Poisson variety, but it is algebraic. So, and that's a notion which I will use in my talk today. So let me recall this notion because it's not as famous as conventional deformation quantization. First of all, it depends on some choices. Namely, we say, suppose that we are given a complex Poisson, for example, symplectic smooth algebraic variety. We say that a normal crossing divisor compactification is quantizable if the four conditions are satisfied. There is some cohomological condition, vanishing of certain cohomology groups. There is a condition on the Poisson bivector field, on the Poisson bracket. It extends from M to the compactification, and it vanishes its tangent, on the compactifying divisor. And the class of that divisor is ample in the Picard group of this projective variety M bar. Then using this line bundle, one can produce certain filtered algebra, which is a semi-formal compactification. So more precisely, the choice of compactification M bar gives a filtration on the algebra of functions with finite dimensional terms. basically it's a filtration by the orders of poles. And this is a general thing. We should keep in mind that if you have something non-compact, some non-compact, say, complex symplectic manifold, and if you want a sort of a theory of D modules or HD modules, quantized modules, then we need to, the choice of compactification defines the choice of what is known as a good filtration in the theory of D modules. All right, so anyway, having a compactification, we have a filtration of the algebra of functions, and in fact, it agrees with the bracket. So we have a filtered Lie algebra. The algebra of functions filtered by these vector spaces and endowed with the Poisson bracket. Now, Kontsevich proved that if you have a quantizable compactification, which is still a quasi-classical object, then one can assign to it an associative algebra over formal series, which he called semi-canonical quantization given a Poisson variety, which satisfy the following property. First of all, it's a quantization. So modulo H, it reproduces what we had before, the algebra of functions. But it also has a compatible with product exhaustive increasing filtration by finitely generated modules over formal series. And this filtration splits as a filtration of modules over formal series. And the last condition is that if we consider the induced filtration on the algebra of functions induced from this one, then we can construct its Ries algebra in the standard way. And so what we get for this ring, so then it consists of finite dimension. It will be filtration by finite dimensional complex vector spaces. So this semi-formal quantization, it's not quite algebraic. It's still over formal power series. It is related to the formal deformation quantization just by simple procedure. You take the H-added completion of the semi-formal. And actually, Maxime proved that semi-formal quantization exists for any affine Poisson variety. So we used a slight modification, or rather restriction. We assume that in all these properties, all the algebras are modules not over formal series, but over polynomials. So indeed, in many examples, this condition is satisfied. For example, for affine X and the cotangent bundle, the example of semi-formal quantization is given by H differential operators. For example, H connections. So H should be H bar. All right. Now, the existence, this choice of a compactification of, say, symplectic, holomorphic symplectic variety, the choice of compactification is nice if you want to define what means a holonomic module. In that case, it's a certain growth condition on the rank with respect to this polynomial ring of the associated graded components of the corresponding module over the quantized algebra. Basically, it's conditioned that it grows no more than the certain power of the index. The nth, where n is a dimension of x. So quasi-classically means that if we consider everything modulo h, then the dimension of the support is less or equal than the dimension of the base, in the case of the cotangent bundle. And then by Gaber's theorem, which says that we have inequality in the opposite direction, the support of the D modulus co-isotropics, we get the condition that with purely algebraic restriction on the growth of dimensions imply that the modulo H, the support is Lagrangian, so this gives a definition of a holonomic module for this algebraic semiformal quantization. We call it just algebraic quantization. All right. Now, in order to work with Riemann-Hilbert correspondence, in order to define, to put it in the framework of deformation quantization, I need not a full compactification. This is too much for me. This quantizable compactification. I need a partial compactification, but partial compactification of a special type. So now I restrict myself to the case of complex algebraic symplectic varieties. Nothing Poisson. So having such a symplectic variety, let's call a smooth Poisson variety a logarithmic extension, or simply log extension, if the difference between these two is a simple normal crossing divisor, and in local coordinates near the divisor, the symplectic form splits into two pieces. So in one, as you see, this d-log divisor, which is given by this system of equations, on this d-log it has poles of order 1, but it can have some other regular part. So in particular, if we take the inverse to this, if we take the Poisson bracket, then the corresponding Poisson bracket vanishes on d-log with the pole order 1. So log extension is non-unique, and but it's in some important from the point of view of Riemann-Hilbert correspondence, important examples. It can be described explicitly, and basically from now on I will restrict myself mostly to the one-dimensional case, to the case of irregular B-modules on curves, in particular most of all to connections on curves with irregular singularities. So I have a complex projective curve, finite subset of singularities. Then what I fix is a certain behavior, singular behavior at these singular points, which is given by the collection of Puiseux, in general, Puiseux polynomials, C alpha, with respect to the local parameter at each singular point. And each Puiseux polynomial appears with certain multiplicity. So from the point of view of classification, formal classification of local singularities, it's known also as the theorem, this corresponds to the choice of diagonal terms in the irregular part in the normal form. So let's fix such a collection, and there are also some numerical conditions, which basically means that such a collection, for example, comes from a vector bundle of fixed rank, something like that. So then, having fixed such a choice of data, which we call singular terms, I can construct or propose a canonical choice of a log extension of the cotangent bundle. And this log extension will be responsible, from the point of view of the Fukaya categories, for the Riemann-Hilbert correspondence for the category of, for example, vector bundles with irregular connections with strike irregularities fixed rules. Okay, what is the log extension? So first consider the fiber-wise projectivization or compactification of the cotangent bundle, which means that we add a copy of the curve at infinity. So then the symplectic form on the cotangent bundle has poles of order 2 in the divisor at infinity, and we need to have divisor in which symplectic form has poles of order 1. And it is achieved by consecutive blow-ups. So we can start blow-ups points which are copy of singular points at infinity, this divisor. And the general rule is that we do a blow-up either at the smooth point of the previous divisor, where the symplectic form has pole of order bigger or equal than 2, or the point which is intersection of two divisors, where it has poles of order bigger or equal than 1. And the starting point, as I said, these are just a copy of my singular points in the divisor at infinity. So making these blow-ups, then we can consider either inductive limit, or we can just stop at some point and keep divisors where the pullback of the holomorphic symplectic form has poles of order 1. So the union of the cotangent bundle, which is an open symplectic leaf, and these divisors, where the pullback has a pole of order 1, is our log extension. So this is sort of illustration, which is these lower divisors. Okay, so next step is to introduce a Planck constant in this story. And here we have an advantage with respect to the real picture, because our symplectic form is still holomorphic. So we can rescale it and obtain a family of complex symplectic manifolds or the punctured complex line. So taking the real part for every h, taking the real part of this, we get a family of real symplectic forms. And now we can do some symplectic topology for each fixed h, or if we'd like, we can work with families. So what will be the good class of Lagrangian submanifolds? If we take a complex Lagrangian subvariety in general, but in this case it's just a curve, so we require that its closure in the log extension is compact and intersect the compactifying divisor transversally in finitely many points. So, and we consider such Lagrangian submanifolds, subvarieties, so they can be singular. So, a small neighborhood of such a Lagrangian is Stein. So then we can consider basically any Fukaya category of our choice. So we can consider, for example, rapid Fukaya category. I call it local because it's associated with a fixed Lagrangian subvariety. So symplectic form is this one, and also the B field is given by the imaginary part of the same holomorphic form. So Maxime explained today in the morning briefly how one can think about these rapid Fukaya categories, partially rapid Fukaya remember his picture with transversal disks, so I cannot reproduce it here. It was very nice. I should borrow his slide. But anyway, what we get some A-infinity algebra, and we can consider, for example, perfect modules over this A-infinity algebra, or for my purposes, for the purposes of Riemann-Hilbert, I will consider finite dimensional A-infinity. Now, the presence of the Planck constant, which is now a complex number, endows this algebra with an automorphism. Basically, just a monodromy about zero with respect to the Planck constant. This is just a remark what we should do in general, but it's more or less clear. The only problem is that in general the choice of a log extension is not fixed. There is no canonical log extension, differently from the case with a tangent bundle to the curves. All right. So then what we have from this, we have a family over C star, family with respect to the Planck constant of some local Fukaya categories which correspond to a fixed choice of a complex Lagrangian subvariety in the log extension of my symplectic manifold. Now let's look at the other side, the wrong side. We have holonomic HD modules, which are modules of this quantized algebra with singular terms at singularities which are not just our given Puiseux polynomials as we would have just in the theory of ordinary D modules, but those rescaled by the Planck constant. So if I divide by 5, it will be different than if I divide it by 7. So it's again, it's due to the fact that H now is a complex number. But now, since I consider HD modules, not just D modules, since I work with deformation quantization, there is notion of a spectral curve because I can take everything modulo H. If I work with D modules, the best I can get in quasi-classical limit is its characteristic variety, which ignores all terms of lower order. But if I work with HD modules, I can keep them. And so I have a spectral curve, or in general, not necessarily conic Lagrangian subvariety. And I can require that, or rather to say that I consider the category of holonomic HD modules on my curve such that the corresponding spectral curve is my given complex Lagrangian variety L, the same L which was in the previous slides. And again, fixed singular terms with singular points. So then we get a category linear over polynomials, and so I denote it like this. So these are my singular terms, this is my spectral curve. And also I can define the similar category for which the Lagrangian subvariety is not fixed. So, and this one is much bigger. It's a sort of a global category of all HD modules. And this one is a subcategory of this one at the level of HD modules. All right, examples of this story, for example, of HD modules are just H connections on the curve. And so fixing L means the same as fixing the spectral curve of the corresponding Higgs bundle, which is obtained by reduction of the H. All right. Now we have one more Fukaya category, which is again category of finite dimensional modules, or the wrapped Fukaya category of the open symplectic leaf of my log compactification. Symplectic leaf here just a cotangent bundle. So I consider finite dimensional modules of the wrapped Fukaya category over this symplectic manifold, again endowed with the real part of the rescaled symplectic holomorphic symplectic form, and the B field, which is imaginary part. And the Lagrangians are the same. It's Lagrangians which behave nicely at infinity, which mean that which have compact closure in the log extension and transversally intersect the compactifying divisor in finitely many points. Now, the first conjecture is that the category of holonomic HD modules with the fixed singular terms and the global Fukaya category are equivalent for each fixed h, non-zero h. Now, this category, for example, for h equal 1 is just the category of holonomic D modules. So this family, in this family, I can fix one constant to be an arbitrary number. For h, like h connection for h equal 1 is just an ordinary connection. So then this statement is basically a statement about family of holonomic D modules, where on the Becky side I put the global Fukaya category of the symplectic leaf log extension, but the proof which we have in mind, it's still obtained by a reduction of the left-hand side and right-hand side to constructible sheaves. There is an alternative idea how to prove it directly by considering the Lagrangian skeleton of this M placed inside of M log, rather the skeleton of M log. But so anyway, so there is such a conjecture. Now, so how to connect, for example, the left-hand side with something which resembles Fukaya? So it's not very difficult. It's just basically a reformulation of classical result of Deligne-Malgrange. So we identified the left-hand side, h equal 1, like holonomic D modules. It's equivalent to the category of constructible sheaves on the given curve with a singular support, which belongs to the union of the zero section, which is a given curve, and positive conormal bundles. Positive means that they have 1/2, not the whole cylinder, but 1/2 of the cylinder, of the closed curves, which I wrote here explicitly. This story, of course, is related and probably is just equivalent to the story of Schende, Riemann, and Zaslow, and also Nadler should be mentioned here, especially for higher dimensions. Because the Fukaya categories which appear in this way, they are invariant of the corresponding Legendrian links at infinity, which obtained from this conormal bundle by intersecting the three-dimensional compact boundary. So this is sort of a sketch of these conormal bundles, some figures on the given curve, on the Riemann surface, which in these closed curves, they take care about singularities of my D modules or connections, vector bundles. All right, this is a remark that we can work directly with contact elements on the Riemann surface, not very essential. All right. Now, if we have an HD module, it can be thought of as a family of D modules which depends on H. H is non-zero, one constant is non-zero. But we can speak about the spectral curve. Yeah? And so then we can ask, if we take H equal 1 and if we take H goes to 0, what's the relation between the two? How to relate this conjecture about global D modules and global Fukaya categories with the local Fukaya category which appeared before, which depends only on the small neighborhood of a given Lagrangian submanifold. So for that, of course, I need to have some result which relates local and global Fukaya categories, and this is the one which Maxim mentioned in his talk as well. So suppose that the argument of a Planck constant does not, the Planck constant does not belong to one of the Stokes rays. This is the definition of a Stokes ray. So basically, there are no holomorphic disks with the boundary on my Lagrangian. So then the conjecture is that there is a fully faithful embedding of the local Fukaya category into the global one. And now if we have an HD module with a fixed spectral curve, then we can apply the global version of the Riemann-Hilbert correspondence with a global Fukaya on the Betti side, no spectral curve. But then we can kind of recall that in the limit as H goes to 0, we get a spectral curve and we get an object in the local Fukaya category. Then it's natural to expect then in the limit as H goes to 0, in some limiting sense, or maybe in the over formal power series, we have an equivalence of the local Fukaya category with a fixed Lagrangian and the category of HD modules which have a fixed spectral curve as H goes to 0. And it's natural to expect, since everything was algebraic, that this will be equivalence over not only in the formal sense, but maybe over the germs of analytic, or maybe better, maybe meromorphic functions at H equal to 0. But the true story is a little bit more complicated on the Betti side, exactly because of the presence of Stokes rays, which divide the H plane, the plane of each line, the complex line of the Planck constant, into the union of Stokes sectors. So, what I would like to do is to take into account what we call the wall crossing structure, which is visible here to those familiar with the concept, but for the rest, I just say that the local Fukaya category, it just gives rise to some data, and those data consist of a collection of holomorphic families of local Fukaya categories in the Stokes sectors. Stokes sector is bounded by two adjacent consecutive Stokes rays. And asymptotic behavior as H goes to 0 is prescribed. It's basically expansion in the rational powers of the Planck constant product with integer or non-negative integer powers of the logarithm of this Planck constant. All right, so then what are the restrictions? So in each stock sector we have this family of local Fukaya categories. Now, if we go by 360 degrees, if we go around 0, then we have the automorphism or autoequivalence factor of the local Fukaya category, which comes from the automorphism of the corresponding A-infinity algebra, which I mentioned before. Now, if I consider local Fukaya categories in the adjacent stock sectors, which are separated by a fixed Stokes ray, then there is an equivalence factor, or if you like, the isomorphism of this considered as a module of the formal series. And this automorphism is of a very explicit or rather controlled way. It's identity plus some upper triangular matrix with integer coefficients and with exponent factors which are derived from my singular terms, from Puiseux polynomials, which were fixed at the very beginning. So what is hidden here is in fact some Chukotty-Waffa type low crossing formulas. So then the claim is that the category of holonomic HD modules with these singular terms and fixed spectral curve is equivalent to the category of such data. There are versions. The weakest version is equivalence to a formal series, but then, as I said, probably this is an equivalence over germs of neuromorphic functions, or maybe even over analytic functions, germs of analytic functions. Now, I still so for illustration purposes, let's discuss briefly the case of H connections, sort of classical objects, also known as lambda connections, depending on how you know Planck constant. So then on the Deram side, we have family of connections parameterized by complex number. On the Betti side, we have an analytic family of representations of the fundamental group. It's the simplest possible case, so regular singularities. So there is a limit on the Deram side, it's a Higgs bundle, but there is no limit on the Betti side. But we have these Stokes data which are described by asymptotic WKB asymptotic, if you like, of flat sections of my H connection as H goes to 0. And these are Stokes sectors, so they are indeed determined by the periods of the Liouville form of the homology classes of the spectral curve, and these are exponents in the WKB asymptotic case if there are no functions. So what do we have? So we have a family of usual Riemann-Hilbert correspondences, equivalences, for every Planck constant. Because if H is not equal to 0, it's just a category of connections, and we can apply the usual Riemann-Hilbert correspondence. But in addition, we have a local Fukaya category of the spectral curve, which is derived with the spectral curve of the corresponding Higgs bundle. So if this spectral curve, if we represent it locally as a graph of the differential of the function, so there are several of them, because the spectral curve has many sheets, then applying this family Floer homology construction, taking the home from the spectral plot to the variable tangent bundle, we obtain on the vector side the simplest possible constructible shift, which corresponds to this type of irregular connection on the Deram side. Okay, so this is just an illustration how we can think about how we can combine conventional story and framework of Fukaya. So just one remark that very similar story appeared in a completely different, I mean it looks like completely different, but maybe it's not. It's a framework of the mirror symmetry for the total space of Hitchin system from the SYZ point of view in the way we discussed it with Maxime in this paper 2 years ago. So, and there we described also what is a log extension in higher dimensions of the wild character variety. So, and again we observed there are Chakotay-Vaha type crossing formulas and many other structures which are visible in the case of wild character varieties, like cluster transformations, wheel crossings, and so on. So probably it's not just a coincidence. So this is an illustration of family theory homology construction which produces the invisible. This is a remark about the higher dimensional case. And now, in the last, how many? 2, 3 minutes? 5 minutes? Right. So I can briefly tell you the story of 2 different situations, because now we see some interesting structures which are not captured by any kind of constructible shift point of view. So here DQ modules, different analogs of D modules, are modules of the quantum torus, and they live on the torus C star and the power n. So one can define many notions which are familiar in the theory of usual D modules in affine space in this framework. It was done by Sabah in 90s, like stain filtration, defunction, direct inverse image, polynomial DQ modules, everything, but not Riemann-Hilbert. Riemann-Hilbert, as you can see, it's much later development by Ramis, Sauer, and Zhang. I already mentioned their paper. And it's in dimension 1 only, and technically they consider vector bundles only. But the DQ modules is quite simple. So, but let's consider one-dimensional story. It's already existing. So it's what for physicists. So what we are dealing with is a quantum spectral theory. So then we can define the sheaf of solutions. Basically, we have 2 variables, x and y, which we commute, so which means that we have like coherent sheaf like on C star with an action of the shift operator. So then the sheaf of solutions, it's a coherent shift on the corresponding elliptic curve. And the role of constants is played by theta function. Now what are the Stokes data? So we have we have an action of the group C star on C with 2 points, fixed points at 0 at infinity. So then we have not just one filtration, but we have 2 filtrations. And so the filtration which will appear, it's filtrations on the sheaf of solutions, similarly to the Lagrange story for usual connections. It's filtrations by rational numbers by coherent subsheaves with quotients which are semi-stables, but this is not a Harder-Riemann filtration because the slopes increase, not decrease. So we call such filtrations anti-Harder-Riemann. And so then the theorem of Ramis, Savoy, and Junk in the case of holonomic DP modules says that the category of holonomic DP modules on C star is equivalent to the category of coherent shifts in the elliptic curves, which are endowed with two anti-Harder-Riemann filtration labeled by rationals and infinity. Infinity takes care about torsion sheets. Now, how all that is related, could be related to the Fukaya categories. At least something of that is clear in general. So, our symplectic manifold is a symplectic torus with a constant holomorphic symplectic structure. So we take the torus compactification, where symplectic form has poles of degree 1. So then, roughly speaking, the global Riemann-Hilbert correspondence is a statement about equivalence of the global Fukaya category with the category of DQ modules with a given Newton polygon. It's a sort of a rough statement. But more precisely, there is a construction which works in general. So it's a family of Floer homology construction, which is now, instead of cotangent fibers, we have a family of C stars inside of C star squared. Now, differently from the cotangent bundles as objects of the rough, they are not isomorphic. And so then we have also, we should handle each fiber with a rank 1 local system. So then, in fact, we have two parameters, monodromy with respect to the variable x and monodromy of this flat connection. So this gives a two-parameter family of vector spaces, homostating in the Fukaya category. It turns out that this family is constant with respect to a one-dimensional foliation. Basically, making a small perturbation with respect to x can be absorbed by a large perturbation with respect to this local system. But the quotient of the two-dimensional torus, which replaces the cotangent bundle to C star, is the same elliptic curve as appears in Ramis, Saloy, and Jean theorem. Then what is left is to understand the symplectic meaning of these anti-Harder-Riemann filtrations. And there is a framework in which anti-Harder-Riemann filtration appears, but probably I don't have time to explain it. It's quite general. So then just for 10 seconds I can keep this slide at the blackboard, but then I move to final remarks. Just one result which I didn't have time to discuss is the Riemann-Hilbert correspondence for holonomic D-modules in higher dimensions in the case of a vector space and in the case of C star in the power 2n. There is an analog of the Stokes data which is described in terms of certain polyhedral decomposition of the sphere at infinity in the case of C star in the power n, and the similar sphere in the case of C star in the power 2n. And the second remark is about the title. In fact, the data which I described before gives rise to what we call wall crossing structures with Maxim. The definition was given in this paper. It formalizes many things, like this scattering story mentioned before by Yao. And it appears in many applications, but the point is that the structures which appear in Riemann-Hilbert, this type of local and global Fukaya categories, it's very typical. This very similar structure appears in the study of exponential integrals in finite dimension and infinite dimensions. For example, complexified Cherny-Simons. Well, in the infinite dimensional case, there are infinitely many Stokes rays, and the convergence condition is interesting. It's related to solutions to acoustic equations mentioned at Stokes. So, and it's related, this wall crossing structure is related to many other interesting equations.
So in your story, you consider complex Lorentz manifold. You mean that you have some complex structure, fixed Lorentz manifold, it's complex manifold.
But it's wrong.
Yeah, so when you took up this rough category, you use this J or different J?
Different.
So you really use common graph with respect to this different or this complex structure?
Well, I use it in order to make a comparison for Riemann-Hilbert. Of course, you can't forget this Riemann-Hilbert, then just hook up some symplectic manifold and forget about the rest. But one thing which is still used from the complex framework is a Biffy, which is imaginary part of the framework. And if I take a complex Lagrangian, the Biffy automatically vanishes.
Yeah, so I just understand which kind of role of these complex structures of this Lagrangian complex manifold. For example, if you consider family free homologies, then you want to put up a complex structure of this family free homologies. Usual complex structure is something like a J of the parameter include Lagrangian is to do this E1 connection. Yeah. In this complex structure you use or have another complex structure, so that's